So case 2, right? We don't know sigma for both of the populations, which is most common case. In reality, sigma is a population parameter, so we can never know that for sure. Now, key important, right? We still need, and this is a common mistake, common confusion, I should say, right? We still need to establish normality. Okay, we still need to be able to say that our estimator follows a normal distribution. Okay, so same rule follows. Right now, because we don't have sigma, right, we use the t distribution, just like with a single, right, just like with a single parameter. Okay, because sigma is unknown. Okay, all right. So once we have, and so t, remember, t distribution is still approximately normal. Okay, our center, it is still at 0. Right, single bar here. Okay, now the only difference here is the way we calculate. Or actually, for this case, right, the way we calculate the standard error is the same. Right, now instead, the only difference is we're just using the sample variance or the sample standard deviation to approximate the sigma. Right? Okay. Now, here comes the hard part. Right? Whenever we use t-distribution, right, we need to calculate the degree of freedom. Now, in a one population, right, remember what the degree of freedom is. The degree of freedom equals n minus 1. Very, very simple. Okay. Now, in a two population case, right, in a two population case, in this situation, our degree of freedom, unfortunately, right, it is very complicated. Right? So it is a very long formula. I'm not going to say anything. I'm just going to write it down here. And there, the big mess, right? All that just to get the degree of freedom. But we need this because with a t-distribution, right? We need to know the degree of freedom, so we know, so we know the proper distribution to look up. Okay, after you get that done, right, then the test statistic, right, is the same as before. So I'll just copy it down here. Nothing much has changed, right? And the confidence interval, same as before. Okay, now the margin of error, okay, remember, right, is the the t distribution times the standard error of theta bar. Let me fix this really quick. T distribution there. It's the t critical value. Okay, so again, this we need. Right, this is where we need the degree of freedom. Right, if we want to look up the critical, well, we need to look up the critical value. So let's give an example, right? Or let's do an example here. Okay, here mu1, our hypothesis is mu1 minus mu2 equal to 0. That, right, in another word, let's translate that. That means population 1, right, mean equals to, right, population 2 mean. Right? So if you think about income, it's just saying like that the average income in LA and New York is the same. All right. So now that's our hypothesis we try to test. So we collect random sample from the two populations, and here we go. These are the sample statistics. Here are the sample statistics that we've gathered. Okay. Again, establish normality. Do we have normal? Is our test statistic going to be normally distributed? Yes, right? Greater than 30 here and greater than 30 there. So we need both of these, okay, in order to proceed. All right. So first step you want to do is calculate the standard error. Standard error, it is, okay, we're using sample variance to estimate the population standard deviation, population variance, I should say. Okay, put that in the calculator and you get 1.606. Okay, and then also just go ahead and calculate the point estimate for the difference here. Okay, all right, A. What is the test statistic? Test statistic is going to be 3.5 over, okay, minus 0, because our hypothesis in this chapter will always be 0. But this hypothesis, you could, if you like, you could change the hypothesis. Okay, but we're just not going to do it here. Okay, that is the test statistic. B. All right, now let's go ahead and calculate the degree of freedom. Okay, go ahead and follow the formula. Okay, pause the video, go ahead and follow the formula and give this a try. All right, and just plug in, plug in all the numbers and see if you can calculate this. Okay, sorry for a little mess here, but that, remember, there's 8.5 squared there. All right, so plug it in like this, and then try the best you can if you can put all that in the calculator at the same time. If not, divide it up into numerator and denominator. Okay, just when you do this, make sure you carry each step, carry at least 3 decimal places. Okay, just to make sure that you don't do too much rounding in any of the middle steps. Right. Okay, now once you get here, you get 65.708. Now, degree of freedom must be in whole numbers, okay? And so 65.708, so we need to round. Now, with degree of freedom, you always round down, okay? Because you want to be conservative with your probability. You don't want to so remember, degree of freedom for t distribution is the higher the degree of freedom, the closer it is to a normal distribution. Right, the peak, right, the more the observation is gathered in the middle, right, and so we don't want to, give the wrong probability. So this will give to 60. We'll round down to 65. So okay, so here's the rule. Always round down. Now in reality, when the degree of freedom gets anywhere above 20, it's not going to make that big of a difference. 65 versus 66, it's just calculation wise, it's really not a big deal. But we're going to be a little bit rigorous here. So the rule is we should always just round down. Okay, fine. Next step, what is the p-value? Okay, so we have our test statistic already, and we have our degree of freedom. Okay, so here is 0. Our test statistic, right, falls at 2.18. Okay. Now, remember, this is a two-tailed test, right? Because our hypothesis is that there's a difference there. So our rejection region is on both tails. So our p-value, right? We need to get both sides as well. Okay. So t distribution is symmetric, so we need both of these, right? So both of these area, right? That's our p-value. Okay. So go to your app, look at your calculator. Now here, right, we're going to our t distribution, type in our degree of freedom, 65. Okay, and then here we get 2.18. Okay. Now on the app here, you have this convenient. It says 2 times the probability. Okay. So we're going to go ahead and use that, and that is 0.3288. Oops, 0.03, and 32, let's call it 329. All right, okay. And so this 3.329, right, that tells us my p-value. My p-value, it is less than alpha, right? Because my alpha is 0.05. Therefore, I reject I guess this is part D now, right? Part D. Reject the null hypothesis. Okay, so indeed we can say that mu1 is different. We don't say greater than or less, or is it greater than or less than. Why? Because our hypothesis is saying, our alternate hypothesis is only saying that it does not equal. Okay, so we don't get to say that it's greater than, we just say it's different than mu2. Okay, let's do another example. Here we have SAT scores of high school students. Now, this is two different populations. So, population one are high school students whose parents are college graduates, and population two are those students whose parents are not college graduates but are only high school graduate. Right? And the idea and the goal is to see if there is indeed a difference in the test score, or sorry, I should say, if students whose parents are college graduated, they have a higher SAT score than students do not have a high school graduation. Okay, so read the question carefully. Now let's start with A. All right. So formula hypothesis, right? That can be used to determine whether the sample data support the hypothesis that the students show a higher population mean math score on the SAT if their parents attain a higher level of education. Okay. Now here we actually have two choices. Okay. All right. So we can either write the hypothesis like this, that mu1 minus mu2 is greater than or equal to 0. Oops, not less than or equal to. Okay, so we have these two hypothesis tests to choose from, right? And now, statistically or mathematically, we can use either of these, and we can perform a test with either of these. But based on the context of the question, though, only one of them is correct. Now, go ahead and pause the video. Take a second to think about why or which one would you choose. Okay? So the correct one is this one. Right? So we will not use this one. Now, why is that? So then I'll read the question again and look for the keyword here is that we want to support a particular claim. Okay, so that is going to be our goal. That's the key word here, support. Right? We want to know if the data supports the hypothesis that students show a higher the students if their parents are have a higher level of education, right, then they have a higher SAT score. That means population 1 is greater than population 2, right? Now remember, we can only support a claim if it's in the alternative hypothesis, right? So this is the claim that we like to support. If I want to conduct a test to support this claim, then I have to use this test. Okay. All right. Now, let's proceed. Before we proceed, we need our sample statistics. Okay, so you can go ahead and give it a try. Go ahead and type in, process these two populations and get the in Google Sheet or Excel, and get the population. Get the sample statistics from there. But I did this earlier, and here I'll just write them down. I'll just write them down here. Okay, remember, be careful with the notation. I'm writing here. This is the variant, the sample variance. Okay, right. Whenever you're calculating using the sample variance, it's going to make things a little bit easier when you're calculating the degree of freedom. So B, what is the point estimate? Okay, theta bar is x bar 1 minus x bar 2. Okay, that is what we observe. That is the point. That is the point estimate. Okay. And then C, we want to compute the p-value. So first thing we need is the test statistic. Okay. Now, in order to do that, then we need the standard error first. Right? So x bar divided by the standard error. Okay. So our standard error, we calculate that here. Okay. So that's our test. That is our test statistic. Okay. Now to calculate the p-value, right? Then we need the degree of freedom first. So now we calculate the degree of freedom. Go ahead and pause. plug the formula in, or plug the numbers in the formula and see what you get. Okay, plug all that in and go ahead and give it a try. And what you should get is 25.34. Okay, and remember, always round down. So this gives us a degree of freedom of 25. Okay, all right. Now to calculate the p-value, okay, let's go ahead and we'll do it on the side here. So what this means is to calculate p-value, I have my 0 here. My test statistic is 1.8. Okay, this is a one-tailed test. My rejection region is to the right. Okay, so that is going to be my p-value. My test statistic 1.8. I only want the right tail. Well, 0.04197. Okay. Okay. So my p-value, it is, so let's do part D, the last part at the bottom here. Right? Part D. Okay. 0.04197. Oh, this is very close, right? At the 0.05. This is still, nonetheless, it is still less than 0.05. Okay, so therefore, because it is less than that, then we reject the null hypothesis. Okay, and then we can say yes, indeed, there is enough evidence to support, right, to support the claim that if the parent has a high school, if the parents are college educated or college graduates, then the student will have a higher SAT score.